I am here in space, surrounded by these funny little dots people are calling stars. But how are stars made? Good question, me. To answer that, we're going to have to start at stage 0, dust. A star starts as nothing but a cloud of dust, called a nebula, which spans many light years. A cloud of dust that, while in this state, will eventually consist of 10 to the 57th particles of dust. To put that into comparison, there's only 2 times 10 to the 6th websites across the internet, 7.88 times 10 to the 9th people on Earth, 10 to the 25th grains of sand on Earth, 3.3 times 10 to the 13th dollars in debt from the US, or the 10 to the 51st atoms that make up the Earth, also known as 1 sextillion, which is still only 1/100,000th of the dust particles that will make up this cloud. Now that we have this massive expanse of dust that makes up an interstellar cloud, the force of gravity from each of the particles of dust will begin to pull on each other, bringing them closer and closer together, condensing the cloud. Due to gravitational instabilities as the cloud contracts, it also fragments. These fragments will also eventually fragment, paving the path for many future stars to form. The particles of dust inside these fragments radiate large amounts of energy. However, only in the center, where the energy must travel through significantly more material, does the temperature rise. In the center, the temperature still reaches about 100 Kelvin, which is only about -278 degrees Fahrenheit. Eventually, the cloud will continue to condense so greatly that the heat cannot leave the cloud easily. Stage 3 is the ceasing of fragmentation, and occurs when the inner region density has become dense enough to where the material is opaque, trapping in some of the radiation. The edges remain less dense and radiate much more freely, making them cooler. Soon, what was once just a cloud of dust will begin to slightly resemble a star and become what is known as a protostar. The protostar will continue to shrinken, densen, and hotten, as well as gain mass until the core reaches a seething temperature of 1 million Kelvin. There is also a giant ring around the protostar that is known as the protostellar disk, which spans about 100 AU in diameter and makes up the material of what will eventually become the planets and the solar system that surround the star. The protostar is still without equilibrium and is continuing to pull mass in and condense. At this point, it is possible to plot our protostar on the Hertzsprung-Russell diagram. Depending on where the protostar is plotted on the Hertzsprung-Russell diagram will determine the star's evolutionary track. This specific protostar evolutionary track is known as the Kelvin-Helmholtz contraction phase. The protostar then leaves the Kelvin-Helmholtz contraction phase and begins on the Hayashi track, in what is referred to as the T-Tauri phase. The protostar's luminosity has lessened and is now at about 10 times solar value. And although this is 14,069 times hotter than McDonald's coffee, it is still not hot enough for nuclear fusion to occur. Due to the amount of heat being trapped inside of the protostar, the rate of contraction slows, and it loses luminosity. Even though gravity is a strong force, it must now compete with the outward pressure caused by the radiation of heat. Therefore, the more energy being trapped in the core, the slower the condensing occurs. These last stages of evolution before a star are much slower than the second and third phases of star birth. Phases 4 and 5, where it is a protostar, take 10 to the 6th years and 10 to the 7th years, respectively. Phases 2 and 3 take 3 times 10 to the 4th and 10 to the... As the star hits the bottom of the Hayashi track, it is now aching to enter the main sequence. The central temperature of the star has reached 10 million Kelvin, which is enough to ignite nuclear fusion in the core. At this point in time, the star is undergoing nuclear fusion in the form of the proton-proton chain. The proton-proton chain goes as follows. 2 free protons collide to form a neutrino and a positron. The neutrino will eventually get picked up in a random lab somewhere due to its inability to be absorbed The positron will eventually annihilate an electron, creating a neutron. It also creates a deuterium. A deuterium will then collide with another free proton to create a tritium, as well as a gamma ray. Two tritiums that have undergone the same process will eventually collide to form an alpha particle, as well as spit out two separate free protons. In the end, you end up with the equation 4 free protons equals 1 alpha particle plus photons plus neutrinos. The end result of 1 alpha particle is lighter than the combined weight of 4 individual free protons, and therefore the energy produced is calculatable with E equals mc squared. Utilized, the equation gives us an output for 4 times 3 times 10 to the negative 12th joules. This is a very small amount of energy. For reference, it's about 1/7 quadrillionth of the power needed to charge a phone, or, if applied at a constant rate per second, would only be 1/10 trillionth of the joules required to kill a man. Although this form of nuclear fusion is not very efficient, the star is still radiating incredible amounts of energy due to the large number of reactions going on within the star at any moment in time. The radiation of energy is key in the fight against gravity that the star is undergoing in this stage. And over the next 30 million years, the star will radiate more and more until the forces of radiation balance out, with the forces of gravity leading to main sequence stardom. The star is now completely balanced with its forces, and is sitting at a central temperature of 15 million Kelvin, and a surface temperature of 6,000 Kelvin. The central density reaches 10 to the 32nd particles per meter cubed, and the star reaches its smallest size yet, of 1.5 times 10 to the 6th kilometer in diameter. Although the 40 to 50 million years it's been since the star became a protostar may seem like a long time, in the grand scheme of things, it's only 1% of this star's life, and for the next 10 billion years, it will be burning like this. By this stage, the star is referred to as a subgiant and reaches 3 times solar radius, as well as being placed in the subgiant branch of the HR diagram. It is within this stage that the star undergoes hydrogen shell burning. This is where the center becomes helium ash due to a surrounding layer of hydrogen burning shell surrounded by a non-burning envelope. After 100 million years, the star is no longer in equilibrium and finds itself in the red giant branch of the HR diagram. The star also begins to burn hydrogen at an accelerated rate, causing a large amount of pressure from the expanding thermal gas. Due to this increased rate of hydrogen burning, the gas pressure from the reaction causes the non-burning outer layers to expand in a force stronger than the gravity attempting to contract the star. The surface has expanded and is now the size of Mercury's orbit. Meanwhile, the core, which is now completely helium-based, has shrunken exponentially. After a few 100 million years, the lack of hydrogen burning is not enough to support the forces of gravity, resulting in a large amount of pressure building up on the helium core, that eventually, over those hundreds of millions of years, heats the core up to 10 to the 8th degree Kelvin. This temperature is important because once the core reaches such a temperature, it is now able to do helium burning through nuclear fusion in the triple alpha process, in which 2 alpha particles are combined to form a unstable beryllium particle, 8Be. Combined with another alpha particle, being the triple, a gamma ray is released, and a stable carbon atom is formed. The triple alpha process, however, only occurs in stars that have at least 1/4 solar mass. It is within this phase of helium burning that we find the phenomenon of the helium flash. Inside of the core, besides the protons and neutrons that make up the helium, there also exists a sea of electrons. Due to the quantum mechanics rule of the Pauli exclusion principle, the electrons in the core are prohibited from squeezing too close together and reach a maximum amount of pressure before resisting against the force of gravity and pushing back. These electrons are known as degenerate electrons, and they supply a force that's name is the electron degeneracy pressure. It is in this degenerate electron-filled core that when helium fusion takes place, There is no rise in associated thermal pressure or drop in surface temperature. So, the temperature rises incredibly quickly and is unable to restabilize the core for a few hours. This is known as the helium flash. Within this stage of helium burning, the star now enters the horizontal branch of the HR diagram. During the red giant phase, there is also solar winds that may carry off up to 20 or 30% of the stellar mass. At this stage, the helium layer is now being rapidly consumed, and a carbon ash center is now forming alongside the layers of hydrogen burning shell and helium burning shell. The non-burning layer on the outside is now expanding again, and the star enters the asymptotic giant branch. By the end of this stage, the size is larger than the previous red giant stage at 500 solar radii. Soon, once again in this stage, the core goes degenerate and is unable to be compressed any further. It is at this point it is possible but unlikely for oxygen to perform in a fourth step of the triple alpha process, in which the carbon fuses with helium-burning shell bordering it. As the star enters stage 12, the radius becomes about 300 times the solar radius. In this stage, the burning becomes quite unstable, and many helium shell flashes may occur. Within these helium shell flashes, the temperature fluctuates rapidly, causing the outer layers to expand, cool, then contract. In the star's pulsating motion, at the peak of each one of these pulses, the outer layer's temperature drops below the threshold to recombine electrons with nuclei to form atoms. Each one of these atoms' formation produces photons, the resulting energy pushing the unstable surface over the bounds of what gravity is forcing it under and out of the star. Within a few million years, almost all of the star's envelope is shot out into space. What remains is two distinct parts: the ejected stellar envelope and the refined carbon core at the center of it. That carbon core that is left behind is known as a white dwarf and is roughly 0.01 solar radii. A white dwarf has a high surface temperature of 50,000 Kelvin and is also extremely dense at a central density of 10 to the 10th kilograms per meters cubed, which is about 10 million times denser than water. There is only one stage left in the life of this star: death. As the star sits in space, it eventually has nothing left to do and cools out, leaving only embers behind.